Our next presentation is how MIPI Debug specifications help me to develop system software. Norbert Schulz of Intel will be presenting. Norbert is a debug tool specialist and software architect in Intel's Software and Services Group with 20 years of experience in embedded tools. He's located in Germany at Intel's System Debug Center of Excellence in Ulm. Norbert is the content owner for MIPI's SISTY and its open source reference implementation. Please welcome Norbert.
Good morning, everybody. Today I'll talk about how MIPI specifications help to develop system software. The background of that talk is that the debug workgroup is working on a new specification targeting software instrumented tracing. And before I jump directly onto the topic, I want to give a brief background on what the debug workgroup does, what it's focusing on, and share with you some good debugging practices that we use to design our specifications after. And then I jump to an end-to-end system software debug solution using MIPI specifications. So I use a couple of specifications from the debug workgroup and combine them to give a system software trace solution. So the MIPI Alliance has a debug-focused workgroup, and what is our charter is that we enable best system debugging support for the mobile and mobile-influenced equipment. So we focus on the debug of the design, not on the functional part itself. So we are trying to get low-cost solutions and define established standards that help the interoperability between tooling and devices. There are specifications that are targeting both software and hardware aspects in a design that deal or contribute to debug. And especially important for the mobile space, there are also specifications that allow you to leverage functional interfaces for fielded or form factor devices for debug purposes. Because what do you want, it solves the problem on how do you get to your debug or trace data when all you have on your device is a functional USB port, for example, and you cannot expose any debug dedicated pin interfaces anymore. So the specifications of the debug workgroup focus around physical interfaces for exporting debug data out of a system, mid-level data protocols for transporting debug data through a design, and also coming up new, excuse me, with the SISTY specification for system software trace, software system debugging. So what do we consider good practices for debugging, especially in the mobile space? First of all, it's important that you understand that debug is an important platform capability as well as the functional aspects, and should be exposed and visible to your customers. The debug support in a platform should scale together with the complexity of the platform itself. And if there's a debug supporting infrastructure on the device, this should not only be available to hardware, but also to software agents to allow software-hardware co-debug. If you don't consider debug a first-class citizen on a platform, you will basically increase development cost and probably time to market for your customers. The second part is all about mitigating the tool's impact on platform complexity. Platforms get more complex with each iterations. And if you don't try to unify your debug solution, this complexity will transfer one-to-one to the debug tooling and environment. So in order to avoid that this complexity moves over to your tooling, seek a unification on your debug environment. If you have several IP blocks creating trace messages, try to unify the data formats. And also the way you capture the data from a platform, from a debug or functional port. Try to standardize on one method that scales to reach everything in your platform, because when you get the data from one interface and into one platform scope tooling, the more coverage of your debug coverage you get with one toolset, the easier it gets to analyze the interaction of these components in your platforms. So if you add an IP block in your design, make sure it gets access to the debug infrastructure that you have in your design, and also on the tooling side, hopefully you can extend that tooling to cover these additional features as well. Again, the more you can cover with one toolset, the easier it is to debug interaction between components. And the third point is about the mobile space, is extend debugging from prototype lab environments into the field on form factor. So in the field, you don't have prototype boards with debug headers, debug pins available anymore. So there are specifications that we have that allow you to reuse the functional ports like USB or Ethernet to capture data in the field. And also have debug features available as a runtime option in retail devices. So don't have debug in retail builds, make it a build option, make it a runtime option, so that when it's necessary, you can get trace and debug data from the field. So this is the example use case that I want to show today as an end-to-end solution for system software tracing on a mobile platform. It's about getting boot logs from a tablet that is a form factor device, so it doesn't have any debug pins anymore, so we have to use a USB port for capturing the data. We're capturing debug data from various areas in the design, in this case focusing on software messages coming from the low-level boot controller or also from the BIOS code on the CPU cores. And we're doing so by utilizing MIPI specification for generating the trace, for transporting the trace through our design, and finally export that onto a USB port. So typical for embedded system devices, we have a two-machine setup. The TS, the target system, is the mobile platform, here the tablet. And you can see in the picture it's hooked up to a laptop, which is the debug and test system that captures and visualizes the debug data. So here you see a simplified block diagram of the target system. So the orange bubbles represent the places where MIPI debug specifications come into place. So on the left side, labeled trace generations, we have the IP blocks that create the sources. And on the CPU cores, on the boot controller, we're executing software and firmware, and this uses the SISTY software instrumentation specification to create trace messages that get then sent to the debug infrastructure of the SoC, called the trace arbiter here. And this is typically a module that has many inputs. It should reach any component inside the SoC design, and combine and merge these independent trace data streams coming from the various sources together into a single output stream using another MIPI specification called System Trace Protocol, or the acronym STP. And by this point in time, we also inject clock time information from the system. So by doing it on this arbitration step, we ensure that all the messages from the various IP clocks are under a common time base, which simplifies the effort for the tooling side to reconstruct the historical message order of the event and to see exactly what happened when, which becomes important when you want to analyze the interaction between different components. So the System Trace Protocol supports two things. It's a data merge protocol for a wealth of inputs, and it provides common trace features like timestamping. I talked to the individual protocols later on in more detail. Then we have this trace message stream now merged together into a single data protocol, and we're transferring that now towards the export of the device to another building block called the debug interface that deals with outputting or exporting the debug data from the device. And here we see another data path that I call here with other functional block and other data. So we have here a second level data merge. So you may now ask, why is this a two-step approach? And the reason is that the STP protocol is a trace message protocol. It's ideal for merging arbitrary length trace messages that are timestamped. But not all data follows that scheme. For example, think about an instruction trace coming from a CPU core. This is typically a highly compressed data protocol on its own that is simply a contiguous data streaming through. There's no message start or message end or a timestamp that you can apply on a particular piece of that stream. It's just additional debug data that you want to get out of to your capture port. So this debug interface, the second level merge, is an ideal place for doing that. And the MIPI specification that's behind it is the TWP, the Trace Wrapper Protocol specification. This is a lower level merge protocol for merging data streams together in an efficient way for output to hardware. And now that we have what is reached combined the debug data streams from all different areas in our design, we finally put them out onto a pin interface. And in this case, we don't have a dedicated debug port, but have to use the USB port, which is a functional interface of the device. And there we use another MIPI specification called NIDEND, Narrow Interface for Debug and Test, that can swap the usage of that port on demand between functional and debug purposes. And you can see here in this case, there's a little switch in the graphics. There's a pin manager that NIDEND specifies either stimulated from the development host site or the target device to change this port that the pins now emit the debug signals and no longer the USB protocol. But this is a more detailed system diagram. So the data path, the end-to-end trace solution that I show here is on the right side, showing the situation for system tracing. But there are other specifications dealing with other debug aspects from the debug workgroup as well. But they're not covered in this talk. But if you go to the website of the debug workgroup, you will find additional specification, for example, for transporting trace data over Ethernet and other technologies. So now looking at the individual specifications in more detail. SISTY, System Software Trace, is currently under development. It is not yet available. The first release is planned somewhere in the second half of next year, and it is aimed towards software tracing. It's a software instrumentation methodology, and its goal is to address the missing standard for software tracing. There are currently only a few established methods for major OSs, but for the wealth of software agents and firmware and controllers, there is simply no existing standard. And SISTY is trying to fill that gap as a specification to be reusable. SISTY is designed to be scalable from small and space and CPU constrained controllers up to a powerful system. And it does so by implementing an embedded system or mobile system friendly method. SISTY splits the effort of creating and analyzing a trace in basically 3 parts. On the build machine, you have your software with the SISTY instrumentation, and when you compile it, it actually also creates what is called decode collateral here, which is an XML formatted information that contains static information for the messages that are created from the software. And by utilizing this static information, we can reduce the compute and bandwidth needs that the trace has on the device if you can't afford much CPUs or space for debug instrumentation. And I have an example on that later on. So what is in SISTY? It's basically 3 things. Since it's a software instrumentation specification, it comes with an API that developers can use to create trace messages. It defines the data protocol that goes, that this API is producing. This is the data that you, if you recall the picture before with the system diagram, you put onto the trace arbiter. And it defines how the XML decode collateral looks like in order to decode the data when it's received on the development system. What is new in the MIPI domain here is that this specification will be backed up by an open source implementation of it. So there will be open source implementation of a SISTY tracing environment that will be available, for example, from GitHub for reuse. And it will be under a liberal open source license so that it can help and accelerate adoption of the standard by other vendors. Here's an example on how this instrumentation looks like using C language. So you will include a MIPI-specific header file that defines the instrumentation calls that exists for the software. And then it's software instrumented trace. So the developer will inject additional calls into the functional software, and this will result into trace messages that are being sent out from the IP block when this software executes. And on the lower picture, we see a trace view receiving these messages, and in essence, one instrumentation call correlates with one message that is received by the development tooling. SISTY can transport both textual and binary messages. So there's the typical printf support, which many developers like and use for software tracing. And there are additional features available, like checksums and custom timestamping. Another important aspect is that SISTY has an I/O channel concept, so you can create multiple I/O connections to the SISTY implementation, and the specification ensures that you can use them in a lock-free in a multi-threaded application if the different threads write to different I/O channels, so to avoid locking overhead in the debug instrumentation. So this is about an advanced feature that we get from the fact that we have the static decode collateral for a SISTY agent in the decode methodology. Many developers use the printf function when they think about software tracing. Printf is a very elegant and powerful function. It can combine static text with variables, format them in a human-readable format, and is quite easy to use. The catch is that printf comes with a cost. It's quite an expensive API because you need to store all that information on the device, and you need to parse this format string, create the output string, and send that data. So it's both compute and space intensive and may not be suitable for small devices or controllers. With SISTY, there's a functionality that is almost like printf, but comes with a much reduced cost. And this is this is what we call catalog messages. It follows the printf signature for the function. So the developer writes almost the same thing as a genuine printf call, but at compile time, the static string actually vanishes from the code. It just evaporates, but gets stored in the decode collateral. In the produced code is only sending the variable part of the dynamic part of the printf, including an ID or a hash value for that string. And it's sent out as a very compact binary message. And if this message is received on the host side, the hash is used as a lookup in the decode collateral where the format string is stored on the development host. And then, at this point, the actual printf formatting happens by using the format string and the variable portion of the payload. So we actually defer the computing overhead of printf to the development host. The device just sends a small binary blob. And in this example here, we, for example, replace a 24-byte string with a 4-byte numeric value. So this turns in a much lower trace bandwidth, lower computation overhead, or if you formulate it different, you can afford more detailed instrumentation of your software for the same overhead. So this was about the upcoming system software trace support. Moving on to the middle layer for transporting the data, STP is an excellent merge and trace protocol that fulfills two purposes. First of all, it allows to merge almost endless independent message channels together. There's a 32-bit space, ID space, where the data is tagged to what channel it belongs to. This channel is partitioned by masters and channels. So there are up to 64K masters, which up to 64K channels each. So STP can combine 4 GB of streams in theory at max. And it does so with a very low overhead because it's a 4-bit nibble-oriented data protocol. And by having these wealth of channels, it's also very real-time friendly. For example, one of the problems when it comes to sending trace data, for example, from a real-time system, is that you typically need to put locks around the message sending functions. Because if you get an interrupt while you send a message, and the interrupted function also wants to send a message, you actually fragment the message that you tried out before, violating or corrupting the data format. With the channel concept from the STP protocol, you have a very elegant workaround to this problem. So if you use more or less the interrupt level on your system as a channel indicator, the data for the interrupted code will appear on a different virtual data pipe than the interrupt handler routine. So there's no data corruption anymore. It's just merging different, and it's up to the STP to transport this data into different virtual pipes and reconstruct them later on the development host in the correct way. So this is similar to the multi-threading support on the SISTY level, but here more or less on a low-level real-time problem domain. So merging data streams is one of the aspects of STP. The second one is that it's already a perfect trace message protocol on its own for timestamping. It contains all the features that you need on a modern trace message protocol. It has timestamping, it has time synchronization support, it has async records that allow you to sync to a streaming, to a live data stream. And it has data integrity checks like CSE, checksums, and everything. The only thing that you need to add from the source side is to provide the message payloads. So STP takes a lot of burden away from the sources when it comes to sending trace messages. All the common features are already implemented on the STP level. The specification for STP is very mature. It's out for 10 years, and gained very wide adoption in the industry so far. You can see here a couple of examples where STP is actually used, is actively used. So the second protocol was the TWP, the trace wrapper protocol, which was what I mentioned earlier when I showed the simplified diagram, the second level data merge. TWP is a pure merge protocol, so it doesn't have trace message semantics anymore. So it's used to combine independent data streams, and it does so in a hardware-friendly fixed size record format. So the data definition is shown on that little picture on the slide below. And so TWP also merges streams together, but it's more focused on preparing the data to send to a hardware output. So it allows that independent trace streams can share one device. So whether a system uses both TWP and STP merge protocols depend on its complexities. Some may choose both methods, some may choose just one or the other. So they're complementary and provide distinct features each. So the last specification that for the solution that I showed today was the data export to a pin interface, and this interface is called NIDENT, Narrow Interface for Debug and Test. NIDENT allows to reuse the pins of a functional port for trace and debug. And the specification supports several pin interfaces from various USB variants, HDMI, DisplayPort, also up to older micro SD card slots. And the specification contains the pin assignment and also how to switch the port between functional and debug usage. Recently, there was an update of the specification that is focusing on USB Type-C. And what is nice about USB Type-C is that it is a cooperation between the MIPI Alliance and the USB standards. So there are USB-defined modes for a MIPI NIDENT port, and it allows you to use a USB-C connector for debug and functional at the same time. So all you need is a breakout board that distributes the signals to the right receivers, and then you can have debug and functional usage of a port at the same time. So here you see a picture on how the capture of the boot log actually works. I can't show actual video here from the presenter screen, but the picture already contains more or less all the important aspects of that. You can see here the platform. It has booted into the UEFI shell, and you can see here the NIDENT port connection. That's an old USB 2 connector that is used in this platform. And since this is a NIDENT port that can switch between functional and debug usage, but not both at the time, so it's currently no longer connected to a USB functional logic here. It's connected to a debug pin interface. So we need actually a capture probe here to convert this debug signaling back into something that can be read over the USB port, can be fed into the USB port of the development host system. For the USB 3 Type-C solution, you would not need this port anymore. All that is required would be a USB debug cable, which is probably available for $20. So you don't need any expensive probes anymore with USB Type-C. Here, it's an either-or solution, so we need the probe. And on the development system, you can see here the trace messages as they got recorded during the platform boot. So this is my last slide. So as a recap, what I showed today is the MIPI Alliance Debug Workgroup releases specification that are highly scalable for mobile and embedded systems, enable low-cost debug solutions like what I showed before with just using a USB cable for debugging, getting debugger or form factor devices, and of course, it tries to establish standards for debug across mobile platforms to allow vendor independence between tooling and devices. So this was just a part of the specifications that the debug workgroup is dealing with. So if you're interested in more, you can go to the MIPI website and to the homepage of the debug working group. And with this, I would like to open for question.
One back here in the back.
Yeah, for some of the software tracing, you said the compiler needed to be modified. So do you have any existing compilers that have been modified for this purpose?
You don't require the compiler to be modified. You can. What we do right now in the reference implementation is that we have a Perl-based source scanner that runs over the source code in addition to the compiler and extracts the static decode information from the source code through an additional Perl-based scanning tool. You can also, if you implement SISTY in your own tooling, you can extend the compiler to be aware of that. But it will work also with standard compilers like GCC, but with an additional tooling that scans the sources to gather the required information.
What are the bandwidth requirements for the trace port so that you don't have trace overflows?
This depends on the trace infra implementation on the device. So on SISTY level, there's no bandwidth control. And SISTY assumes that since it's sending traces at software speed, that the debug infrastructure of a device can handle the bandwidth. If it can't, it's up to the implementation of the debug infrastructure how to react, whether it creates back pressure in the design or if it goes into a data drop mode. But that's up to the implementation. But on SISTY level, there's no bandwidth control.
Any other questions? All right.
Okay. Thank you.
Thank you.